come up to 4. Oops, sorry, I went backwards tonight. When n is equal to 4, then you plug into 4 minus 1 is 3. So you go up to a value of 3. So that's why you pick the 0, 1, and 2, 0, 1, 2, 3, which corresponds to S, P, D, and F. That's why you have a 4S, 4P, 4D, and 4F. Now, when n is equal to 5, we actually pick up a G-type subshell. And when we start to, when I say find homes for electrons, we're going to see that we don't actually ever populate a G-type subshell. It stops at the F-type, or the L value. But it's possible. So this actually is written kind of from the lowest energy up. Sorry, the lowest energy, and then as you go down, increasing energy. But when n is equal to 1, we have one type of subshell, and it's L is equal to 0, which is an S-type, 1S. When n is equal to 2, we have a 2S, 2P. When n is equal to 3, 3SP, 3S, 3P, 3D. And it's equal to 4, 4S, 4P, 4D, and 4F. And it's equal to 5, we pick up the G. And it's equal to 6, we pick up an H. Kind of exciting times. And it's equal to 7, we pick up an I. Do those subshells exist? Yes. Are they occupied as electrons or in their ground state? No. Okay. So whenever you see the word energy level, I'm hoping you're thinking N. Energy level, principal energy level, that's the same diff. So if you have an energy level like n is equal to 4, where you have principal energy level n is equal to 4, you have an S, P, D, and F. As I've drawn them, that's correct. Actually, the thing I handed out, I lied a little bit with regard to increasing energy as you go up. I'm going to have to kind of fix that probably on Wednesday. But if it's in the same principal energy level, S is always the lowest, and then P, and then D, and then F. Okay, in the same principal energy level. All right, so let's look at that third quantum number. It's called the magnetic quantum number. Okay, so magnetic quantum number, M sub L. And so on the sheets that I gave you, actually, for each little orbital, which is a box, I've actually, underneath that box, and I did this the other day, written out the M sub L value. There are rules for M sub L, and they go like this. Actually, there's 2 rules, and they mean the same thing. You could say it one of 2 ways. Values of M sub L are actually bracketed by the value of your L. Just like values of L are bracketed by the value of your N. They go, let's see, which one do I like better? I think I like that second one. The middle box is going to be 0, and then going on either side, it's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, etc. All the way up to plus or minus L. They're rules. So I don't have to recreate the whole thing here. That's why any S-type subshell, whether it's a 1S, 2S, 3S, 5S, obviously is going to look like this, and its M sub L value is simply 0. Okay? Because that L value for S is 0. So 0 all the way up to plus or minus 0. This is 0. For a P-type subshell, regardless if it's 2, anything beyond 2, it's got a P-type subshell. It has an L value of 1, and P's, hopefully you would tell me, have 3 boxes. And the M sub L values of these guys are 0, have to do the middle one first, minus 1, plus 1. That's it. Any D-type subshell is going to have 5 orbitals, 5 degenerate orbitals. Oh, my boxes get so bad. M sub L values, pick the middle one, just kind of like symmetry. I think it's very pretty. Minus 1, plus 1, minus 2 plus 2. The last one we need to worry about is the F-type subshell, which of course has 7 boxes. And so we need to have 7 M sub L values. You would tell me the F corresponds to an L is equal to 3. So that means we have 0, plus or minus 1, plus or minus 2, plus or minus 3. I got it. Okay, that's kind of how that whole thing works. It's not that hard. So, how many different orbitals, that's the boxes, can be found in a particular subshell? So, here we go. I mean, we did it right here. When it's an S type, it only has 1 orbital. Okay. When it's a P type, it has 3 orbitals. Why? Because we actually have 3 M sub L values. 0 and plus or minus 1, because P is 1. D type, L is equal to 2. So then we have 5 values. We have 0, plus or minus 1, plus or minus 2. An F-type subshell corresponds to an L is equal to 3. So that gives us 0, plus or minus 1, plus or minus 2, plus or minus 3. So that's why we get 7. Not bad. So if we kind of back out, those were subshells. What if we back out from the subshells into the principal energy level? Well, you can do them a couple of different ways. The last slide I have coming up is kind of a quick and dirty to say how many orbitals you have. To me, the sheet that I gave you, and actually that's why I wrote the sheet out, is I literally said, like, when n is equal to 3, I counted on that sheet. We have, when n is equal to 3, we've got what? This sort of situation, when n is equal to 3, so I just counted boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9. When n is equal to 3, we have 9 orbitals. Okay? Like I said, I have a kind of a thing showing. Actually, I picked on, that's exactly what I have here. You may be asked a question on a test. The principal energy level, n is equal to 3, how many orbitals are there? You would say 9. The little trick I'm going to show you is, what is 3 raised to the second power? 9. That's the thing. When n is equal to 4, guess what? If you count boxes, you get, what's 4 raised to the second power? 16. Isn't it fun? It's just adorable. Okay, so there are 9 orbitals here. How many electrons can be, if you fill a box or an orbital, how many electrons can you get in there? Just 2. 2 in each, exactly. So if we were going to entirely fill n is equal to 3, how many electrons could we fill with? 18. Exactly. Is there a bunch of writing in this one? Yeah. Oh, not too bad. Okay. Very good. So those are the kind of the hint that. Those are the 2 main hints I'm going to give you at the end, the last slide in this part. I am like, when we did the other problems, I'm into drawing a picture, and it seems like with this sort of electron, we're going to call them electron configuration, electron quantum numbers, I am into kind of drawing a little picture before I answer the question. That's what I think helps. So, we have the first 4 principal energy levels, and then the second column, of course, the 0, the 0, 1, the 0, 1, 2, 3, 0, 1, 2, 0, 1, 2, 3. Those are the S, SP, SPD, SPDF. So somehow, if you're already kind of familiar with this material, you're going to want to translate what you know to kind of a quantum number. Then over here, this column right here, these are the M sub L values. Respond to that L value. So remember, as we talk about these boxes over here with specific M sub L values, these are where two things. These are the the energy, the amount of energy. This is zero energy, and this is going up in energy. This is the amount of energy that electron would have. This is also where the electron is as it is associated with the nucleus. I hesitated to use the word orbit because although we say electrons orbit the nucleus, you know they don't orbit like planets. So this is kind of the space where the electrons are found. And so the way this works then is there is kind of a shape to this space. So let's talk about those shapes. The two shapes that I want you to for sure be able to kind of find your way around are the S. If it's an S orbital, whether it's a 1s, 2s, 3s, 5s, or whatever, the electrons are buzzing around in the nucleus in a spherical shape. Isn't that cool? If it's a p-type, we have to have three shapes or three orbitals, and it's going to be like a dumbbell shape, and where the two lobes of the dumbbell come together, that's where the nucleus is. So remember when we see a diagram like this, the bzzz, kind of looks like a buzzing beehive? Okay, those are locations where the electrons can be. So the denser the kind of bzzz, the more likely electrons are to be there. So this spherical shape is of an S-type. So orbitals that are an S-type subshell. Now this is actually 1s, 2s, and 3s. And hopefully you can get a sense for, in the center there is the nucleus. So one of the things we've been talking about is that 1s have lower energy than 2s, and then 3s have the highest amount of energy. Not only that, but if you get up to 3s, you're not only more energy, but you're also further from the nucleus. So those two things are happening. So you can kind of see the blue is farther, that's a 3s, than the red, which is the 2s. Versus the little blue there is 1s. Okay, so S are spherical, P's are dumbbell shaped. Now, this is what I meant by dumbbell shaped. So like I said, they have two lobes, and at where the two lobes come together, that's where the nucleus of the atom is. That's so cool. So in other words, like the probability of finding an electron that's in a p-type subshell there at the nucleus is 0. That's the p-type. Now, if I were to ask you like a graph, you probably would give me an x-axis and a y-axis. And then as some of you guys know, if we want to go 3 dimensions, we're going to get a z-axis. And so kind of along those lines, each of those, we have a piece of x here. We have a piece of y here. We have a piece of z here. Isn't that cool? I just think that is so cute. Well, the D-type, we need to have five spatial regions where electrons can be that correspond to these 5 orbitals, and here they are. They get a little more complicated. So for an F-type, we need 7, and they look like this. 1, 2, 3, 4, 5, 6, 7. So this is like those electrons that are hanging around an F-type subshell. They are going to reside in one of these 7 type distributions around the nucleus. That's crazy. My next slides just kind of look at each one of these individually. So there's the S, spherical, the P, dumbbell shape. Now you can see it's a little better. You can see if we do an X, Y, Z, we have the X-axis here, we have the Y-axis going in and out of the board, we have the Z-axis going up and down. So we have a piece of X, a piece of Y, over there, a piece of Y, and a piece of Z. And then here is, a different one for the D and the F. So this is individual piece of X, piece of Y, piece of Z, and you would tell me if I completely fill a p-type subshell, how many electrons are we talking? 6, yep. So this actually would be how the 6 electrons, if we completely fill a subshell that is a p-type subshell, beginning with n is equal to 2, how those electrons would be buzzing around. Well, this is the D type. You can tell I got 5, 1, 2, 3, 4, 5 corresponding to these 5. M sub L is equal to -1, excuse me, -2, -1, 0, +1, +2. And beginning with n is equal to 4, we pick up the F-type orbitals and then anything above. This is just a stick figure showing you 1 and 7. So the way this figure is the first column, hopefully somewhere along the line you're going to be recognized. If you see it spherical, it's an S-type. Notice the going up, we're going up 1s, 2s, 3s. And here are P-type subshells, 2p and 3p. So I mentioned the idea of if you have a P-type where you have 2 lobes and at the center of the lobes is the nucleus of the atom where those orbitals are associated with. It's called a nodal surface, and I mentioned 0 probability of finding an electron there. So the P-type has 1 nodal surface, or 3 nodal surfaces. And there's a D-type nodal surfaces as well. Well, the one thing we didn't talk about today, but I know we talked about it Friday, is what are the values, or I already have it up here. I told you that that last quantum number, you can have +1/2 and -1/2. So if I have an up arrow like this, we're going to call that +1/2. And if I have a down arrow like this, we're going to call it -1/2. I can draw a nice, humongous, beautiful box. Take order onto electron, plus electron going up, shown going up. I have a little video. Be kind of like the metals that can be magnetized. And if we have orbitals where all electrons are paired up, that means no magnetism, or no magnetic field. If instead we have, I'll go ahead and make it a P-type subshell, and we're going to talk about why this is. If we have a P-type subshell where you have a bunch of unpaired electrons, then we can have magnetism. I'll say magnetism, yes. Okay, in unpaired electrons, and we call this paired electrons. So here is a OpenStax figure that's showing you can see the rotation here. This would be what, clockwise here, and counterclockwise here, creating a magnetic field in opposite directions. Okay. If you want to put a little star on here, put vocab. It's a famous vocabulary term. Pauli's exclusion principle. The exclusion part comes in that electrons would be excluded, electrons hanging around the same atom would be excluded if they have the same set of 4 quantum numbers. It's not happening. You're never going to have electrons around the same atom that have the same, any 2 electrons with the same zip code. Pauli's exclusion principle. An outcome of Pauli's exclusion principle actually is this. This is Pauli's exclusion principle in a picture. What this is showing is one orbital. Now, if you picture that one orbital, that one box, it will have that orbital will be in a specific principal energy level. That orbital will be in a subshell associated with that principal energy level. That orbital will have a particular M sub L value. But what makes those electrons unique is that One will have a plus 1/2 and one will have a minus 1/2. That's Pauli's exclusion principle. And in your homework that's going to be due Wednesday, it's actually, now that I'm thinking about it, I wished I would have done my answer key a little bit different. But it proposes, what if instead of this M sub L value, M sub S value having a possibility of plus or minus 1/2, what if it had 3 values? And so I wish I had gone something like, no, that still wouldn't work. I don't know. I think I just went A. You could make it a visual B, and for some weird reason, we're going to make it impossible to see there. Because I thought, well, what if you go thirdsies? No, that won't work, because then you'll end up with 6 instead of 3 possibilities. So anyway. Okay. What else we got? All right, kind of finishing up here then. If you have an S-type subshell, you would tell me there's only one orbital, M sub L is equal to 0, and in that box we can shove 2 electrons so we can accommodate 2 electrons. If it's a P-type subshell, we can accommodate 6. If it's a D-type will have 5 orbitals, so put 2 electrons in each of those, we get 10. If it's an F-type, then we have 7 orbitals. If we completely fill those with 2 electrons each, we're talking 14. So these were kind of the little things I was talking about before. Now let's read it carefully. What if you were after the number of orbitals, those are boxes, in a particular subshell? Well, since the rule is this one, then actually for any type of subshell, but this is kind of silly because you probably already know that if it's the most common S, P, D, and F, you have memorized we have 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. But otherwise, you can plug in the value for L, take it times 2, and add 1. What if taking that same idea a little bit further, what if instead of orbitals we wanted electrons? Then we would take the number of orbitals, which is 2L plus 1, and then we would multiply it by 2 because we could put 2 electrons in each. This is the one that I kind of started out when you guys told me 9 was the answer to the number of orbitals and n is equal to 3. I said you take 3 and you square it. So if you want to know any principal energy level, you just, how many orbitals there are, take the principal energy level number and square it. What about then how do you find how many electrons you can accommodate in that principal energy level? Multiply it by 2. 2 times n raised to the second power. So those are just kind of, but I already told you, I kind of draw pictures when I'm answering these questions. I draw pictures to doodle, to kind of kill time. So just to kind of summarize, because on Wednesday, we're going to actually start using all of these rules, and we're going to start finding homes for electrons according to the rules that we've talked about. So electrons are located in orbitals. We use arrows to represent the electrons, and the most we can fit in any orbital is 2, and if you have 2 in there, they have to have opposite spins. So you have all sorts of kind of little kind of brain teaser sort of questions that can be asked about this concept, about the way things work. Orbitals then are grouped into subshells, and starts with letter D. What do we call it? For instance, these orbitals, if they're in the same principal energy level, it sounds like a bad term, but it's not. Degenerate, yeah. Yeah, we call it somebody being, they say, you're being a degenerate. So, yeah, things would be degenerate, just means they have the same energy. Subshells of orbitals then are organized into energy levels. Cool. I kind of got a chuckle out of this because I was like, you must show your work, which is, this is just kind of silly for this. I told you no calculators for your Unit 4 exam. If you use a calculator, I will take it from you because I think you have something in the calculator. Show your conversions. Like, really? Are you serious? There's no conversions. Do use factor label, show the intermediate, starting intermediate and final. It's rounded to the correct number of significant figures. This so is not applicable to these homework problems. But it's just as easy to put it there than to not put it there. So yeah, that's as far as I wanted to get today. So pick up here on Wednesday. And don't forget to be getting primed for your unit exam on Thursday. Please.
I have a quick question.
Yes.
Okay. For this one, it's saying use has dissolved, which I did on this one. It took me like an hour.
Look at that.